I will proceed now with use case 2. I will start by sharing the presentation received by Dell. At any moment and point, if we do have any questions from the online participants, please do let us know by using the chat. We will highly appreciate it. I'm sharing also the screen. Am I? I am. And I would like to call a representative from Dell to proceed with the presentation. It's going to be Aidan. I don't think that I have to give another introduction again. So here you are. Thank you very much in advance.
Some of you in the room have been listening to me talking non-stop for the last 4 years, and unfortunately you have to listen again. So I'm here to represent use case 2, which is the Dell Technologies use case. Now, I have to admit, I haven't seen these slides, so I actually don't know what's in the content. However, I'm pretty confident I can talk about the use cases. I've been working on it for quite a number of years. So I suppose everybody is probably familiar with the brand Dell. You know, I can imagine everybody here. That's not Dell there. But before it was Dell in Cork, it was originally EMC. So EMC is originally a storage company. So we build storage arrays in the site in Cork. So I think some of you have been to Cork, you've been to Dell in Cork. You've seen the, the scale, the size, the factory that we have. And what we do is we build storage arrays. That's what we do. So in Cork, then I'm not sure if it was there when I think we had a GA there last year. Was it last year? I think it was. But from when I started in EMC, which was approximately 10 years ago, to today, the site has pretty much transformed. And when I started, like we had overflow car parks, we had, there was just a huge amount of personnel. And the site today is much leaner in terms of people. And one of the reasons for that is the adoption of robotics and cobots. So if you come to the site in Cork, you will see robots and cobots zipping around the place. And so when I started, you could wander into manufacturing day or night. Today, you're actually limited in terms of the access you have. You can only go in maybe for 30 minutes a day, and it's badge access. And the reason for that is the robots and the cobots that are going around the place. So we have a significant amount of robotics. And with that amount of robotics, as you can imagine, is huge amounts of data. So our robots are generating a lot of data, and we want to benefit from that data. We want to learn, we want to optimize, we want to avoid. There's a lot of benefits to analyzing the data, looking at the data, and one of the issues you could say with the data is it's not free to use. As in, it does cost money to analyze that data. And what we want to do in glaciation then is to reduce, to harmonize, to optimize the amount of energy that we're using to analyze our data. And to that end, we developed a validation framework in Dell, and where's the old laser pointer? Does it work? Okay. So I was trying to figure out the laser part. Just there, all right. So we built this platform inside our lab in Dell, and I think, you know, if you're working on the project, you're familiar with the validation platform, you're familiar with the integration platform. We have, I suppose we have internal to Dell, we have this validation framework, which is built on Dell hardware. So when you go into our lab, you'll see the you mightn't see the actual robots inside in the lab, but you'll see the far edge, the near edge, the cloud environment. You'll see the robots outside in the manufacturing floor. And on top of this cloud edge platform, which I think was alluded to in use case 1, and it'll be discussed in the other use cases as well, we have our glaciation platform. So the concept here in this diagram is supposed to illustrate the idea of data being ingested and being able to analyze this data both real time at the edge or at the far edge, which would be on, we'll say, gateways or devices within your use case, or perhaps on an on-premise data center or within the cloud. So our use case essentially is enabling analytics at various phases in the cloud edge. Next slide, please. That's right. So I won't go into the details of glaciation because this is perhaps not the right forum for it, but based on the research that was carried out within the project, applied to the Dell use case, we have seen both a concrete reduction in power or energy in our processing of cobot data. So we've seen both a concrete reduction and also we've seen, based on simulations, significant reduction for large-scale deployments. And I've talked to some people here today, and we'll probably have discussions later on as well, about this concept of scale. And scale is really where I see the benefits of glaciation becoming very apparent. And, you know, as I said, at small scale, and again, back to what we're familiar with, you're familiar with the validation club, we've seen concrete reduction in power, but when we scale it up, we start seeing massive amounts of power reduction, energy reduction. So that's where we see the next phase of glaciation going, and this is what we've seen in our use case in terms of the benefits. As I said, both concrete and at scale, we expect to see significant benefits. So, yeah, so the as I mentioned earlier, like what we're doing really is analytics. So this is deploying analytic workloads on our cloud edge. We've seen, you know, very good figures in terms of the actual results from the analytics that we're doing. So this is where we might be looking at robot data at real time, make predictions based on that data. So we see, you know, pretty good figures there, and we've seen concrete energy reductions in terms of the power or the energy required to do the analytics for our use case. So next slide, please. Yeah, so we've looked at, and it kind of ties in a little to the exploitation phase, at least for Dell. I think the other use cases are probably a little different. But in Dell, and specifically in the research that we do in Horizon Europe, or state-funded research, is really to look at the research that's being done by our partners and how we can you know, maybe exploit that research, how we can learn from that research. And we've been pretty lucky, I think, in glaciation in terms of the research that's been done by our academic partners and being able to adopt that research into Dell. I've just made two references, you know, just, you know, there's so much research, and, you know, I could have listed a full slide, but I just picked two pretty much at random there, the ant colony optimization being one, and like, you know, certainly we see tremendous opportunity from that research and adopting that research. Like, I suppose Dell's strategy is we would take the research, we would apply the research maybe to the manufacturing, but not just that, but we also apply that research to our products. So as I mentioned, Dell makes storage. We would expect to apply the research being done to our storage or to, you know, to our gateways or whatever, you know, and that could be infrastructure products, could be software. So, you know, my point there is it's not just the benefit to the use case, but also the benefit to the wider Dell portfolio that we would expect to get from the research. So yeah, I think the rest of it really is to do with, you know, we've seen good functionality in the platform, we've seen good performance, and I know internally we are discussing how to use glaciation. There's a significant interest in terms of sustainability, in terms of data management, in terms of privacy. You know, the list goes on in terms of the strategic validation and the strategic benefit to Dell. So I'm quite pleased to say, at least for us, the project has been tremendously useful. Next slide. So yeah, what we've learned, and again, I've kind of hammered home on this a few times, it's scalability, and glaciation really shows benefit at scale. And we need to really take advantage of this for glaciation too. So such a project is planned. Certainly it's my hope that we'll be here again in 3 years at another final event, because I think to really leverage the work that we've done, we need to scale it up and scale it massively. So that's my core message. We've seen, like, as I mentioned, our validation testing, at least in Dell, has shown concrete, real results. And these are results that we can use, and, you know, they're of benefit. But to really, you know, really, I suppose, show what is potentially there, we need to scale, and we need to scale big. Again, these are some of the you know, some of the learnings we've made, fine-tuning, use of simulation for validation, optimization, etc. This, you know, these are all, I think, valuable, important lessons that we've learned. And as I mean, you know, as I said, there's a lot of the research has been of tremendous benefit inside Dell. So next slide, please, Bacchus. Yeah, so path towards the future. So what we want to do next, I think, was I think MEF were kind of asked the same question: is what do you do? Where do you go next? And our pathway is slightly different, but it's really taking the research that we've done and looking at our portfolio and determining where we can exploit, where we can build on the research, as not just for manufacturing. Like if you look at pretty much every area, supply chain, you know, or data management products, you know, the list goes on of areas that we can apply this research within Dell Technologies. So that's I think that's about it. Baptist, is there another slide? Yeah, so I'll pause there for questions if there's any questions or comments.
Yeah, hey, thanks for that. Have you looked at the energy cost of the algorithms themselves?
Yes.
Oh, sorry. Yeah. Have you looked at the energy cost of the optimization algorithms themselves? Are they insignificant compared to the savings?
Yeah, I suppose for our validation testing, we looked kind of what I would consider simplistically. So it's either energy saved or not energy saved, and that was our perspective. And actually, it's a good question. We might dig into tomorrow as well, and it goes back to the theme of the whole project, which was to do with harmonizing rather than saving. And we didn't specifically look at the cost of those optimization algorithms. It's not a case we weren't interested, it was a case we just didn't have time. But even if there is a cost, I would be interested to look at it in terms of the harmonization. Are you better off? Even if they do cost you, does it result in a benefit globally or benefit? So, yeah, to answer your question in a long-winded fashion, which is something I'm known for doing, we didn't explicitly look at the costs of the algorithms themselves, but in our validation testing, we did look at the overall saving.
Thanks. Thank you.
Thank you for the question. Thank you for the answer.
Thank you for explanation. Could you please give some information about infrastructure, homogeneous or heterogeneous, about the pod, the lifetime of pod, how long pod run, and how many pods did you test?
Yeah. And I'll be calling on my Dell colleagues at this point to give me details I don't have. I know we've done testing of 20, 30 pods, which is maybe a little small. And based on my own simulations, we kind of need to scale that up to about 1,000 pods. And that's per node, so it's really need to scale it up to start seeing the real good benefits. But
the testing started with the heterogeneous cluster. Okay, what we shared with you guys. So first our testing was with the default,
Default scheduler.
Yeah. So that time the benefits were kind of like in the CPU memory size were good benefits we saw, but not really great in an energy views. Then we tried to adapt your try to sync up with LUH for your some scheduler. So that also we got a good benefit from CPU, RAM, memory part, and plus energy wise little slight. But then we have to extend our test for get better energy results. So then we extended with the swarm optimization and colony optimization and IMOC. That paper actually I don't know that paper, but the ideas, ADAS ideas. So we scale our testing.
And how did you measure the power consumption using Kepler or a power meter?
Yeah, using Kepler and then the Prometheus. Actually, Prometheus helped us a lot to get the real figures and to get them the exact time what you need.
And how?
Kepler.
Yeah. And how about pod lifetime? For example, 10 minutes, 1 hour, 2 hour, 1 day.
With our custom scheduler, I'm not sure. Yeah, yes. With the default scheduler, it runs for say more than 5.5 hours. It can run up to 9 hours. It depends on your testing and how your parameters. But with the custom scheduler, also I think it's the same amount.
I mean the lifetime of pod.
the execution time.
Yeah.
The execution time is it's more than 5.5 hours.
5 hours.
Yeah, plus 5 hours.
Thank you.
Thank you.
Great. I think
Yeah,
we can call it a use case. And
yeah.
you all agree?
So, yeah, I don't think there's any other questions there now, and I'm sure you'll hear my voice again before the day's out.
Thank you very much, Aidan. Let's proceed quickly to use case number 3, SAP. Indeed, SAP. Supplement Dr. Jonas Buchler, who is going to give us the presentation of use case 3. I will proceed with somehow sharing the screen as I'm handing over the microphone. Here you are. And in the meantime, I would like to point out, give me a second, that he's a senior AI scientist in AI privacy and security at SAP, works on SAP Foundation model, and has contributed to the use case, leading also use case 3, demonstrating how privacy-preserving analytics can be implemented in practice, enabling organizations to gain value from data while fully respecting confidentiality, trust, compliance with EU regulations, and additional things that he would like to point out to us. So please feel free to start.
I think that's already a great introduction, so I will not point out many more further things, but I will ask you to skip ahead. Yes. So the use case is called privacy-preserving cross-company collaborations. The main problem that we're tackling here is that valuable data is locked away and hidden in data silos and cannot be shared directly, right? For AI training, analytic tasks, having access to a large pool of data, a variety of data is really important. So it's critical to get access here. However, right, while cross-company collaborations promise to leverage such data and bring it together, the issue is that you cannot easily get access to it due to privacy problems, regulatory requirements, competitive concerns, and other alterations you can think of. And the solution in this space now is to simply protect the data in use and beyond, right? Easier said than done, of course, but the main technological enabler here is something called privacy-enhancing technologies. This encompasses a variety of solutions. Here our main focus is on computation on encrypted data, mainly with the help of secure multi-party computation, MPC, as well as anonymization, which is satisfied by digital privacy mechanisms, abbreviated as CP here. And the idea is that this fosters the collaboration by protecting the data. It only reveals the insights over the data. There's no need to reveal the data itself, right? You can reveal the output of computation, not the data. And this is already the main takeaway of the whole presentation. I could stop here. However, I've brought more slides. It would be a shame to not show them, so let's continue. I want to give a bit more detail on the use case again and clarify the scenario to give it a bit more concrete touch. Here we're looking at an industry setting, right? There's an asset manufacturer that produces industry equipment like pumps or maybe some manufacturing equipment, production pipeline equipment. And an equipment user utilizes its assets in its production process. Now, the asset manufacturer's goal is to learn statistical insights about the asset health, monitor behavior, analyze sensor data, and ideally also improve the design of how the machine should function, work, and how it's being used, right? And information about this is available at the asset users, but not necessarily the manufacturer of those assets, because they require the data from the different users here. However, while the equipment users are interested in improved design, maintenance, and services, they are unwilling to share production data directly, right? Again, it will come potential concerns or because we put potentially production relevant information, their backlog, their production throughput, financial information that is linked to how much production capacity we currently have or are expected to have. And here we still look into how we can provide a meaningful analytical task or meaningful AI task here, predictive maintenance of assets across those users that takes into account the measurements across those different asset users is the use case we are considering here. And we want to predict fairly as early as possible here to reduce maintenance costs or downtime and improve the overall efficiency. And the enabler for this is privacy-sensitive technologies. Mainly we're focusing on common stack, open source, cloud native, MVC stack, and I will talk about that a bit more later. So next slide, please. All right, there's a bunch of objectives, the contributions, the use case provided here. I will just quickly skim it. So one objective is a flexible, open, well-neutral architecture. And here our contribution is secure collaborative computation built on those open source cloud-native Carmine stack. Like a C framework. Another objective is basically trustworthiness. Here we can say that due to the privacy preserving collaborations, we also aim to help here. And finally, development of privacy preservation and privacy preservation models technologies, right? Definitely completely fits here where we're looking at privacy-sensitive technologies and integrated like single public for privacy. And finally, also, we want to test demonstrate the effectiveness, and we do so in the legislation environment and provide the amazing privacy preservation aspects with high accuracy tree-based model training that combines MPC and DP. And we have research to support also inference on large language model that is secure and private, meaning it does not reveal the query running potentially updated ways that you were also saying to model service provider, as well as ensure that the output is doesn't the information of the training data. All right. Let me give you a bit of a preliminary overview about what those technologies are, what is MVC, what is DP in this context, and why can we combine them. So as I actually use TANGO stack for secure with path computation and Google DP library of privacy, but also potentially others. These technologies provide orthogonal computation protections. Right? Input privacy, which is the error going from left to right, and it's forward computation. It only reveals outputs results, but no input data. This is achieved with MVC. This is great. Are we done yet? No. We are also interested in output privacy, which prevents backward interference, right? Even the information that you revealed in an MVC fashion cannot be more about the input data than you want it to. Because otherwise you can simply compute the average of two values. You know your value, but you don't know the other person's value. But if you know your own value and the average of them, you can reverse basically just a little computation and say, okay, I know the average, I know my value, his value must be this, or her value must be that. And to prevent something like that, we also want to achieve output privacy in certain scenarios. And those are the ongoing protections. No. And the use case impact here is that we protect data in use, right? Computational encrypted data allows to take data while it's being processed. This goes beyond protecting in transit, like transport security, and at rest, like advanced encryption standard. And we can also combine paths, right? This is also the idea from the slide before. MPC for input privacy and DP for output privacy. Those are orthogonal protection guarantees, and we can combine them. Also, we can have practical privacy technologies. Purpose-specific designs and trade-offs reduce the performance of various of privacy technologies. I jokingly say we can make things secure and private, but if you don't do it accurately, go in a meaningful way, you also do incur large performance overhead, you make things slow and inaccurate. So it's important to balance those things, right? To ensure that the MPC DP solution you've designed is as efficient as possible without incurring major overheads. One approach here we have looked at is tree-based model training for predictive maintenance, which runs in seconds instead of hours. So the main idea that I will just briefly sketch here is there are solutions that do the entire computation in MPC, meaning the entire tree is trained in an encrypted fashion. All the training data is encrypted, and the entire training data is used in all steps because they cannot easily be scaled. Otherwise, that would leak information. How much data you already use in which step is only some kind of information that can help you with frequency attacks. So if you do that in that kind of way, that would truly require hours of computation, terabytes of data that has to be sent to the different servers running this computation. However, one of the simple trick we use is that we simply use data independent tree structures, something called extremely random trees. Instead of using one tree, you use dozens of them, and to ensure that the split on which attribute and on which threshold you use is selected independent of the data, right? And then you simply have to count how many samples per user falls in that's called bucket, basically, which leaf corresponds to a given decision. For evaluation, you can securely aggregate those histograms and then reveal them if you want, or keep them secret. Now, what we have is a data independent, publicly available tree structure, and so you can still run secure inference on that by not revealing, for example, the counts of the samples that land in which tree, which gives you like a probability of which classification you should use in a certain scenario. This is the rough idea. We did also have the different approaches that have different trade-offs here, but the main takeaway is we can, with such trade-offs and clever design sense, task-specific realizations, get down the runtime and the overhead significantly. Also, we can fault the collaboration, right? We protect distributed cross-company data and only reveal the computation that we jointly did and the joint result, right? The idea is, as I mentioned at the first slide, we increase the pool of the available data by letting others participate in not data sharing, but what's called inside revealing, right? We don't reveal the data to any third party or any subset of the parties. We let them compute on their own data or compute on encrypted data, and thereby protecting data. Furthermore, we can add a different privacy on top of that to ensure that the output doesn't reveal much about the input. In the tree-based example, you can simply add noise to the counts of the tree leaves to ensure that a single sample doesn't have too much impact on your evaluation, thus satisfying the idea of the privacy. Overall, it needs to improve accuracy and reduce costs, and we also simulate to validate that way. It's one approach simply to the existing data set and reduce the amount of data that's available. You can see the accuracy drops, right? It's hard to validate it by increasing the available amount of data because simply you probably want to solve here as well. But the reverse direction, you can easily validate that more data is better, which is also, of course, not a major insight, but a common sense idea. Finally, the idea to reduce costs. There's a NIST report from, I think, 2016 about the economic impact of predictive maintenance, and they note that the failure to provide meaningful predictive maintenance or simply the cost of not having such manufacturing equipment available to preventive maintenance issues. It runs in, I think, roughly 100 billion. That's a decade ago. And if you have even small accuracy improvements, right, a fraction of the 100 billion, it's still kind of a lot of money. So the aim is to improve it here, and also validation measurement showing that you can get additional accuracy improvements again simply by using more data, and especially something like predictive maintenance, where the goal is to trace a failure, right? It's typical outlier. 98% of the time it works, but then it doesn't. And if you find those outliers, those points where it doesn't, you need more and more data to find a fraction of those single samples that go. And you want to figure out what happened there and improve your design accordingly. And next slide, please. So what we have learned is collaboration helps collaboration, right? Not only, of course, with the new project here, but also we collaborated with Bosch on cloud native MC framework carbon stack as a foundation for cross-company collaboration, right? So we collaborated with them to bring this MPC framework or to try and develop this MPC framework and contribute here to make the vision that we have here for cross-company collaboration reality by ensuring that there's MPC that can satisfy cloud-native architecture solutions. And this is one aspect here. Another thing is regarding managing price-sensitive technologies. Again, not major insight, and most people are sure, but those price-sensitive technologies can be complex. So use of interfaces, abstractions, and say building blocks are here really important to follow. If the tool is so complicated that even though it has super amazing capabilities, but it's too hard to use or easy to misuse, hard to parameterize, or you can achieve yourself with foot super easily, people will not use it. So if you properly extract away as much complexity as you can, for example, for building pre-computed FSC programs for specific tasks, if somebody is not an MC expert, there's an issue that they come for. You have to have, for example, fixed loop. You cannot reveal the data flow because that might be information about the data. If you have, if secret is true, then stop always logification. Simply the runtime will already reveal if secret is true or not, right? So this would be a simple one-bit mixture, but you can expand this to more serious things. And this also must be accounted for. And ideally, one approach would be to provide here some same helpful approaches, like we did with our tree-based model. So there's also trade-offs of privacy and accurate performance. There's no optimal one-size-fits-all solution, right? For given tasks, you have to do the work, and have to look at it, and have to ideally improve it. Otherwise, there's, of course, general purpose solutions, but it might not be the fastest solutions available. And since energy efficiency is also a major concern here, this is an interesting aspect one has to take care of. And next slide, please. All right. Our path towards the future is that we really believe in private expert technologies and that they will gain more importance, right? Especially in the age of AI, where they don't want to even reveal too much about the training data directly, right? In fear, they don't want to reveal what private information that might have been used there. And just last Friday, Google released their first, it's called GALA family, it's the first model that's large language model that's been fully trained with typical privacy from the go, not 5U, but pre-trained 1 billion parameter model. There's of course some efficiency downsides, so they think they say performance-wise it's comparable to a model that has been released 5 years ago, specifically GPT-2, but still it shows no signs of normalization, unlike their other gamma model families. There's an interesting technical report, it's called Volt Gamma, if you're interested in that. So that's just some interesting proof point. And of course, we want to further build about our paths, our results, our research, our learnings here. Regarding power stack, or specifically the MC's stack and privacy technology here, this was started by Bond's research, but it's now a Linux Foundation project. And MPC is a member of the steering committee here, right? Again, to drive awareness, to drive uptake, to make it more available to a broad set of people, to push this cross-company privacy with learning collaboration possibility further on the road. And here's a quote from our director open source program, Peter Giese. Our engagement with CarbonSec underscores our commitment to privacy-preserving technologies and secure data sharing. These are crucial for enhancing data-driven business collaborations for SAP customers and transforming the future of cloud security. Computational encrypted data at scale goes beyond traditional methods, like protecting sensitive data at all times, even in use. And with that, I only have one slide left, and that's just it. Thank you.
Any questions, points? Congrats on the extremely engaging presentation and on the last slide. Physical participants, online attendees, any questions at all? Not any? Then, although you have pretty much described everything, just in 2 lines. Glaciation, SAP, next day, what's going to happen next day?
Like I mentioned, we still want to further push those privacy technologies. And of course, there are major aspects in the privacy learning aspect here of the GLACIATION platform and can easily integrate and link into here, right? One future idea would, of course, be to have the extension not only of placing workloads across nodes within one cluster, but across multiple clusters in the MPC fashion. So you can distribute it to different cloud providers to ensure that MPC approach is truly sound, because you have to ensure that the computation that runs on multiple servers is system in such a way that the servers cannot easily coordinate with each other, cannot easily just share their current state. Because revealing the communication state that is encrypted, so-called secret kernel, would basically bring the accuracy guarantee. So that would be an interesting future point.
Thank you very much for these 2 lines. And so we can proceed with our final use case. Thus, we will head to the grid with IPTO, the independent power transmission operator from Greece. It's a pilot case, our 4th. Substantial telemetry and edge micro data centers need a new green index that guides workload placement towards locations with more low emissions energy. So analytics are not just fast and secure, they are cleaner. I will give the floor directly to our dear friend and partner, Orestis from IPTO, to proceed with their presentation. And I know that there is also a video, so I should start.
Just the slides up.
Okay, excellent. Then I will go and share my screen. In the meantime, you can.
Well, to prove our dedication and investment in the glaciation project as IPTO, I'm COVID positive this morning, so nevertheless I'm here I'm very happy and excited to talk about our contribution to the project. Okay. Yeah, so the name of the pilot case, Smart Internet of Things for Enhanced Grid Efficiency and Resilience. Who are we? We are IPTO, the transmission system operator, the unique, the single one. In Greece, we manage all the high voltage lines from production to the distribution operator. So what's the problem that we're addressing through glaciation? Well, our SCADA systems, which is the telemetry system that monitors all our equipment from, as I said, production all the way to the transmission lines, all the substations, the transformers, everything is equipped with sensors, hence the Internet of Things part of the pilot. So all these systems generate large streams of data, all kinds of measurements, voltages, currents, power throughout our system. And this data needs, it would be very useful if it could be processed almost in real time so that we can detect any anomalies in operation and be able to step in and do any kind of activities that would mitigate the problem before it gets worse. Also, predictive maintenance is a big thing here. If the data indicates that something is about to break down or there's a high probability to break down, again, we would like to see it in time, get some kind of warning and step in and do maintenance before things get worse. So what is the opportunity? Well, we have all these local sites, all these, you drive by, you see these big transformers, all these sites are owned by us in Greece. So we have our local sites, they are secure, it's a critical infrastructure, it's very important to maintain security there. They are well connected via our own fiber network. So there's good communications, and more, they are located very close to renewable energy sources, solar farms, wind farms. Usually there is a TSO site nearby directly connected to that. So we have all these good conditions locally to be able to, well, these sites generate the data and there are very good conditions there to actually process the data at the same time. So this is where glaciation steps in. We have this idea of placing micro data centers at our sites and do the analysis locally using, ideally, the available green energy at the time and a place where there is excess green energy produced. Next slide, please. So why glaciation? Well, it's a data-centric platform, and our use case is all about the data. As I said, large streams of very critical data produced that need to be analyzed, and it's suitable both for real-time, or almost real-time analysis, but also for long horizon, like analyze the stream as it comes, or safely store the data to batch process them at the later time. So IPTO joined using the hop-on process. So we joined almost at the half point of the project, maybe even a little bit after. And we were joining an established consortium with very strong partners. This was very important for us. What are the features that we're looking for? Scalability, adaptability, efficiency, transparency, all things that are explicitly stated in the beginning of the project. Again, we are critical infrastructure. Anything that happens, potentially with regards to the system, any kind of integration in the system as critical as power grid needs to be handled very, very carefully. So all these features are very important. We can consider integration with the power grid. Then 2 points, why glaciation, but also why, well, as a use case, we bring the energy infrastructure sectors to the front. And also, as a use case, we're a fairly good test bed for sustainability, because as I said, we have to do with green energy, lowering CO2 emissions, and also the distributed computation part. As I said, we're looking into doing computations at the large number of local sites distributed all over the country. So distributed computation is very, very kind of relevant to this use case. Next slide. Okay, so now we'll just walk you through what the use case looks like. So as I said, we have the telemetry data generated by sensors of the local sites. In the middle sits the glaciation platform, and in this case, in our actual validation kind of setup, we have 3 micro data centers located at different parts of the country. Okay, so they're geographically spread. So the glaciation platform is basically in the middle, takes the sensor data and distributes it to the micro data centers for analysis. Next slide. Okay, so here we have a time series. This is power generated at a specific power transmitted through a specific part of our network. So we want to have a rolling window into a specific time interval of the time series, and we want it analyzed. So during our validation time setup, this window is cut into a chunk, platform takes it and decides to send it to one of the micro data centers for analysis. It could end up 1 or 2 or 3. Next slide, please. What happens there? Well, at every micro data center, the chunk of data goes to analysis, depends on the exact task. One thing we did is just anomaly detection using open source deep network called Moment. So Moment actually predicts, uses part of the time series to predict the rest, and if the prediction is too far from what you actually see, that's considered an anomaly. And you can fine-tune that to your specific case. So every chunk is basically marked as normal, or if not, then it can be marked as unknowns, something weird going on here. And there's a constant stream of that going through all the micro data centers. Next. So here's where the green part, comes into play. So based on our own SCADA data from each one of the locations that the micro data center is in. So according to our own SCADA, our own measurements, and according to the sort of central information that we maintain regarding how much renewable energy is consumed at every given moment, we assign at every location what we call the green index. So this is a number from 0 to 1 or 0 to 100, depending on how you will see it. If it's below 50, that's bad. It means that actually at this point in time, the specific geographical location is consuming fossil energy that has been transmitted from somewhere else, which is the worst case scenario. And if it's high, if it's almost 100%, means that the specific location is actually consuming green energy that is generated somewhere close by, which is the best case scenario. So this serves as a signal to the platform to decide where to send it. Ideally, you want to send it towards the micro data center that has high green index. Next slide, please. This is from a paper we presented in IIIC 2025 this summer in Crete. And in that paper, the kind of like key result is that we saw that, according again to our data set, covering renewable, like ratio of renewables in the national energy consumption, and according to our SCADA data, the green index correlates negatively with CO2 emissions at the national level. So the higher, as I said, the closer the green index is to 100%, the lower the CO2 emissions. So according to this previous, please, premature firing of the changing of the slides. So according to this, we can use the green index as a proxy for CO2 emissions, right? We want high green index, we want tasks to be executed during high index values. Now you can do it. And now you can play the video as well. So this is an actual kind of like a visualization of the validation task. So you can start seeing here that the telemetry task is kind of like slowly being consumed as we go. Chunks of the data are getting pushed. The platform distributes it. You see that it consistently refers this micro data center because it's actually connected to a local renewable energy source. These two are kind of both kind of bad, but they switch. Sometimes one of them is worse, the other is better, and you can see that the task stream kind of like alternate between them. Because we are consistently, we're pushing tasks to this one, you can see that the utilized green index, which means, the green index at which every chunk is actually processed, is consistently around a whole 10% better than the actual mean green index among the data centers. And this, given this 40%, and this is like close to 50, that corresponds to a 20% better green index used, which is like one of the key KPIs that we have for this project. Next slide, yeah, I think we're done. I just replayed 1 more. What have we learned? Well, internally to begin with, one of the surprising lessons was how actually, tight is the control within our own organization of the data, especially the staff. So we have to go through a lot of administrative and bureaucratic, jump through a lot of hurdles on this kind internally to get the data, but we did actually manage to get our hands on it. And, going forward, this it wasn't more than that. It's understandable. Again, this critical infrastructure, right, is like really, really sensitive data. So it makes sense that there would be a number of gates that one needs to go through to get it done. Second lesson that was kind of important to us was exposure to modern DevOps, all kinds of technologies that have to do with the integration and validation of the platform. We, as the research department of ICTO, had some exposure, but seeing them in an organized manner end-to-end was like very important to us. Shout out to Fire on this smiling at me. So on a higher level, a more concrete understanding of the potential of edge computing. I mean, we had some idea that yes, this makes sense for us, as I said in the beginning, but seeing it in practice, going through all the steps, seeing what it involves, what we can potentially get out of it, this was like all our eyes in some sense. And finally, the development of the green index. This was something that came up organically through our efforts for glaciation. It was something very kind of important because it showed us that we can, like, once we managed to get access to our data and handle them in a correct manner, and doing all the things that need to be done to maintain to protect this data, then so that we can actually extract a lot of extra value out of that data. And green index was like, kind of like a very important step to that. Next slide. Oh, okay. I actually had it's sort of updated. Okay. So what do we want to do? More experiments, more data, more simulated locations. Very important to us. Now that we have this setup both on the platform, also in simulation form, we want to scale up and see what we get out of it. Because again, we discovered a lot of things we didn't know before we actually run these stats. We want to explore further the green index and maybe other indices and decide what kind of extra value can we get out of our data. And further projects on edge computing and beyond glaciation and build on top of what we learned from glaciation. This is also something that we're actively pursuing. Thank you.
Thank you very much. I kindly invite the online participants to clap as well. Any questions? Too many. Let's.
The green index, like, it seems really interesting. Do you think like other TSOs will adopt the green index?
That's a really good question. So we're actually, we're active member of NSOE task forces, which is the European organization of all the TSOs. So there are active task forces on data centers and the grid.
Yeah.
Huge strategy. Ireland, of course, being at the forefront, both in a good way, but with somebody.
Yeah.
So yeah, something like the green index, we're discussing within that forum, and I think there's a lot of potential for it there.
And the green index, do you reckon, or do you think you could apply it outside of data centers, like I'm looking across the house, even,
Yeah, I mean, data centers are just really, with the intensity that they're consuming energy and with the ability to shift workloads either in time or in space, which is like a factory cannot easily send a part to be manufactured somewhere else, but the cloud service can easily, decide to execute your query here or there or later, maybe. So data centers are somehow like a very good use case for this. Yeah. But the green index is just a measure of, as I said, locally available green energy. Is there a surplus of power locally that comes from renewables, something that does happen quite often, and can be flagged somehow so that a consumer can take advantage of it.
Yeah. Okay, very good. Thanks.
Thank you. As far as I understood, you selected the data center according to last time slots, a time window.
A time window is just a little task. It's just a piece of work that we sent to do. So it hasn't. Does that answer your?
In one slide,
Can you go? Yes, I can. But where? Yeah, just sit here.
No, before this, I think.
Before?
Yeah.
Here?
Yeah, no, before this. Yeah, here.
Okay.
You selected the last time slot, as a time window and selected the data center based on this time window.
No.
Okay.
So this time window is just, as I said, it's just a piece of data that needs to be analyzed. So where it goes is actually decided by the green index. This would be something completely, this would be, I don't know, any kind of analytical task that generates a lot of distinct, independent chunks.
Okay.
Yeah.
And how long is the length of this time? 10 time slot, 50, 100?
It depends again on it depends on what you want to analyze for. So if you want to do predictive maintenance, maybe pitch cover, I don't know, a day. But if you want to preemptively try to detect some kind of instability in the grid, some kind of stability in frequency or voltage or something, then it might be actually something quite shorter, like a couple of seconds. So it depends on the task, right?
Okay. You selected based on try and error, yeah?
To be completely honest with you, this was, because we really just wanted to stress test the orchestration. This is not really something we could have just run, random noise and do some tasks on it and just consume cycles. We took advantage of it to actually, use our real data, but the whole objective was basically to test the orchestration.
Maybe I have one suggestion since I work on time series prediction, and in one of my paper, I consider the length of the time window to predict the next time slot.
Okay.
And there is one theory, minimum information principle theory.
Mhm.
And based on that, we can define the optimal length of time window to predict the next time slot.
Mhm.
Maybe it will be useful for your.
Oh, yeah, absolutely, absolutely, absolutely. The anomaly detection task that I described, what you say would make a huge difference. In actual performance, if you can get a good theoretical estimate with some guarantees about the window, it would be absolutely decisive in what you see in terms of performance. It's just that in this case, because as I said, we wanted to test the platform and we needed the fine tuning of the anomaly detection was secondary. But in practice, it would be very important.
Okay, thank you.
Any other questions, points? In that case, thank you very much.
Let's put my mask on now.
Put your mask. Let's do it, and let's do the very same for all use cases, because now we have ended pretty much the journey. We have started from where the compute moved and why. We have moved to the privacy and compliance issues, and where we had the enforcements and the changes and the different tools, and we have understood, we have reached and understood what has actually changed in energy accuracy reliability via the activities that the project has performed. And I think that there is nothing better than giving the actual stories from the actual pilots, from the actual use cases, to any type of audience in order to properly understand what we have achieved as a project. I will proceed with a pre-final section of this day, actually this event. It will have to do, it will be the collaborating for impact, where we will present, we will have the opportunity to briefly see additional efforts made by other projects, by projects that we're like calling them as sister projects or that are members of our cluster. During the last 36 months, we have collaborated with too many projects, actually, with projects that have received funding under the very same call topic, but others that have received from other call topics, but had some similarities or had the overall same somehow strategic impact and wanted to achieve what we tried and hopefully successfully achieved. Unfortunately, we do not have the representation of all the sister projects, and this is unfortunate and fortunate, because otherwise we will probably miss lunch. So that's even better, to be honest. We have participated and we have worked together with them, and we have co-organized activities, webinars. We've participated in final events. They have done the very same. We are quite lucky to have such collaborators, such friends and colleagues and sister projects. We have been sharing information, knowledge, deliverable reports, contact lists, things starting from communication, dissemination to actual implementation that have supported all participating projects, and that have it's actually proving to the European Commission that projects can work together, especially if they have similarities. Partners can go beyond consortium level, and this is also what the European Commission wants and needs in reality, because at the end of the day, they simply want to avoid two things. They want to avoid putting projects on a draw and never going back to the actual exploitation, and having too many projects doing the very same things or similar things without finding ways and bridges to collaborate. We have achieved both, I believe, with a very concrete sustainability and exploitation plan, and with a tremendous collaboration with these other third-party sister projects, whatever you would like to call them. Today we have our dear friend and communication, dissemination, exploitation leader of ENCRYPT from APELS, Stelios Sirotokritou. I will give you the floor right away. He's participating online in order to provide us with a brief presentation of ENCRYPT. Let's call it like a 10 minutes or as many as you like. You will not miss lunch. So please feel free to take the floor, screen mic, and provide us with some information about your project, with which we have worked fantastically during the last at least 15 months. That was also the period that I was active in the project. So I give you the floor, screen and microphone. Thank you very much for finding the time and for attending the whole event today, even online. Thank you. Let's try and see if we can hear you. I will use my technological skills in order to.
You should be able to.
We cannot yet, so just give me a second.
Okay, hold on. No.
Now I think we do.
Hello, hello.
Hello, hello.
Okay. Thank you, Bambis, for the introduction, and good afternoon, everyone. And thank you for giving me the opportunity to present the ENCRYPT project. My name is Stelios Erodokridou. I am a project manager at 8Bells Limited here in Cyprus. And I worked as Bambis said, as communications and exploitation work package leader for the ENCRYPT project. Today, I'll be giving you a brief overview of the project, outlining its key objectives and partnerships. And if you want, I can talk a lot more about our technologies as well. So the project was originally submitted 40 years ago under a cluster 3 call focused on privacy-preserving technologies. The aim was to support solutions demonstrating high scalability and strong applicability in cross-border federated computation involving personal data. Indeed, the core objective of the ENCRYPT project is to transform the way sensitive and personal data is handled and protected, ensuring GDPR compliance across a variety of sectors. So given the widespread concerns surrounding the processing of sensitive data, we chose to apply privacy-preserving technologies across diverse use cases, specifically in the fintech, healthcare, and cybersecurity domains. I'll just put a small parenthesis and just emphasize that we're focusing on privacy-preserving technologies. And the essence of these technologies is in the name, privacy preservation. You probably know this through the GLACIATION Project. That means working with data that have personal information in them, but allowing for us to still carry out analysis on them, whether we're working with differential privacy, homomorphic encryption, trusted execution environments. These are technologies that allow us to use personal data, but still be able to retain their privacy. So the ENCRYPT project was supported by the expertise of a consortium comprising 14 partners from 8 different countries. The project was coordinated by Access, which is an SME based in Athens. The consortium brought together a diverse group of organizations, one startup, which is called TrustUp, which served as our technical coordinator, 3 SMEs, 2 large enterprises, and 8 research institutions. And within the project, some partners focused on developing core technical components, such as the privacy-preserving technologies I mentioned earlier, while others have played a key role in designing the use cases and leading the validation of the ENCRYPT platform. We also had partners, one partner which provided us with the ethical and legal aspects of our technologies, ensuring that we're still GDPR compliant with our solutions. So why was ENCRYPT needed? There's various challenges that are going on in the world which inspired the ENCRYPT project and its vision. As we know, in today's digital era, the processing of personal data presents growing challenges due to increasing volumes and sensitivity. For medical records, medical records could unlock personalized treatments. Sensor data could improve autonomous vehicle safety, and cybersecurity logs can help prevent attacks. So these are data that we can use, but it's important to retain the privacy of this information. It's important to retain the anonymity, not only the anonymity, but the privacy of patients when conducting research on medical data, for example, and any other kind of data that may be created. For example, automotive data, for example, the electric cars that can drive themselves, that still retain information on the person that is actually owning the car. And so it is important to retain the privacy of the data. So this is where privacy-preserving technologies come in. They allow us to carry out secure data analysis while still protecting privacy. Despite these technologies face significant barriers in terms of scalability, integration, and usability. And this is the challenges that ENCRYPT tried to overcome. So again, a small parenthesis. These are advanced technologies that we're working with. They involve cryptography, encryption, and they're not basically technologies that a regular user or a researcher of a biomedical field, for example, can implement and use by themselves. So ENCRYPT tried to have usability and the user in mind when building its platform and making these technologies available to them. So while a range of technologies have been developed to enable data processing without compromising privacy, trying to balance maximum utility with strong privacy protections and allow for their adoption in the real world remains limited. This is largely due to performance constraints, lack of user friendliness, as I said, and uncertainty about the appropriate level of privacy required for specific data sets and outputs. So the ENCRYPT project addressed these barriers by developing advanced, scalable, and practical privacy-preserving technologies. And I'll present these in the next slides. Sorry. So all our technologies can be seen on the left. So these are fully homomorphic encryption, trusted execution environments, differential privacy, combination of homomorphic encryption and trusted execution environments, acceleration services as well. And we also have some privacy supporting tools, namely our advanced data processing tool, pre-processing tool, knowledge graphs, risk assessment tool, an AI recommendation engine, and also the front end and back end services of the whole platform. And as we can sort of see on the left, everything is brought together by the ENCRYPT platform, and they allow users to use our technologies. This for a short introduction. I can go through all the different technologies later if you want. So the main objectives of ENCRYPT were to improve the performance and scalability of these technologies, making them suitable for GDPR compliance and cross-border data processing. Other main focus was user friendliness, helping all types of users better understand and adopt these technologies. Interoperability was also a priority, ensuring that data can be processed securely across organizations and sectors. Another key goal was to support European data spaces and contribute to standardization, especially in areas such as cyber threat intelligence. And to ensure practical impact, all our solutions are co-designed with end users and validated with a real-world use case. Finally, we committed to strengthening the open source ecosystem and supporting the upskilling of researchers in the space. So, for example, we carried out 2 hackathons on privacy-preserving technologies, presenting them with the various technologies that were developed by ENCRYPT, and also showing them various skills that they could learn to anonymize the data sets and also prepare them for privacy-preserving analysis. This timeline here represents the journey of validation phases. ENCRYPT went through 4 validation phases, including 3 use cases and an external validation case. The ENCRYPT platform has been validated through various use cases. In the health domain, we worked with hospital partners to process patient data securely for clinical and research purposes. In finance, we aim to safeguard sensitive banking data while enabling advanced analytics. In cybersecurity, ENCRYPT aims to enhance the secure sharing and analysis of cyber threat intelligence across organizations. As external use cases and validation of our work, we also worked with the electrical power system in Greece, as one of your previous speakers showed for glaciation. And we also validated our results, I believe, with the GLACIATION project. So throughout the project, we learned key lessons. Integrating diverse privacy technologies was challenging. It requires careful attention and interoperability and working with users. User-centric design was essential. And also it was important to balance performance with efficiency. And that's why we have a hardware acceleration aspect to our platform, where code can run on GPUs and they can run much faster. This was especially the case for the fully homomorphic encryption component, because a lot of encryption and decryption of data has been carried out there. And GPUs were basically, the code was basically ported to run on GPUs and run faster. Another key insight from the project was community feedback. We met throughout, from the beginning of the project till the end, with various stakeholders, not just other research projects similar to ours, but also end users that could possibly use our technologies, and various public organizations that gave us feedback that we basically took into account as we developed our technologies and our platform. So with regards to collaborations with the ENCRYPT project, ENCRYPT is a member of the EasyNet initiative, which brings together various European funded projects to collaborate on AI and cybersecurity matters. It aims to raise awareness and exchange project results and promote open science relating to AI and cybersecurity. Below you can see the partners of this initiative. And some key aspects of collaborations that we had throughout time was joint seminars with the trustworthy project. We had two joint white papers with various projects. So this was the first one, which you can find on the ENCRYPT website, along with these partners. And the second one was with the other partners there. And we also collaborated with GLACIATION in various ways too.
Great. Thank you very much, Stelios.
I have one more slide, if possible.
Yes, please.
So looking ahead, ENCRYPT will continue to innovate. We're hopefully going for a second ENCRYPT and making these technologies available to users, and also incorporating new technologies, new post-quantum technologies as well, to be available for users in the future. And thank you very much for your attention. If you have any questions, feel free.
Thank you very much for your time, to be honest, and for your overall support and for the opportunity to work together as cluster, as a sister project. Thank you very much, Stelios. Now,
thank you,
we will conclude with the actual first presentation of this clustering section. And I will proceed to the next one, giving the floor to Leonardo Cherubini to conclude today's event, so that we can join lunch, which otherwise we will not be able to do, but also because in reality we have gone through all the different points and the different sections and the different elements of what we have achieved during the last 36 months. Thus, everything to you.
Thank you, Babis. I know that what I'm going to say will try to say it, but I will skip a part of my final remarks. just because others better than me have highlighted the outcomes of the glaciation project, and which is the contribution that project like glaciation brings to Europe's digital transformation. What I can skip is to thanks all the project partners for their dedication that have been driving force behind our achievements. And thanks to also to ENCRYPT project who joined us today. Thanks to all who followed us online. Your participation is essential to ensuring that the conversation we start here can spread further and generate new opportunities. And thanks to Legal Council and to Babis for the organization of the event, for hosting the event in this wonderful location. And well, finally, I invite you all to stay with us for the networking lunch. That is an occasion to continue the discussion this morning and to build new connections. Thank you. Thank you. Thank you. Thank you very, very much.